Okay, we left off after 17b, so we are looking at 17c. And again, we're going to look at the binomial random table in our book. So we're talking about this table right here that says cumulative binomial probability. Now let's notice it tells us right here that this gives us the probability of an x value less than or equal to some number. Okay, well, what we're being asked for on this particular number, part C, is the probability of that x is 4. Not that x is less than or equal to 4, which is what the table gives us, but that x is 4. Now let's remember up here, n was 5, p was 0.5. So when we want to find the probability of just a single number using the table, we've got to find the probability that x is less than or equal to 4 from the table, and then we want to subtract the probability that x is less than or equal to 3, one less than this number right here. And the reason for that is, if we look up here and we think about this giving us the cumulative probability, x is less than all of these bars on the left, then if we just want to get the probability of this bar right here, we need the probability of this amount over here, and we want to subtract it off of this entire amount to the left, and that will give us the probability of that single bar. So since in our instance back here, n was 5, p was 0.5, we want to find from the chart the probability that x is less than or equal to 4, and we want to subtract off the probability that x is less than or equal to 3. So if we look things up on our chart, the probability that x is less than or equal to 4, so we'll have n is 5 and 0.5 for p, less than or equal to x equals 4 will be 0.9688 for the first part of our computation. And we want to subtract off the probability that x is less than or equal to 3. Again, let's go back to that table. So if we look at 3 in the same column, 0.8125. And then let's allow our calculator to do that computation. We get 0.1563. Let's now look at number 18. X is a binomial random variable with parameters n equals 10, p equals 0.6. We want to find the mean and the standard deviation. All right, so if we know we've got a binomial random variable, these computations are actually fairly quick and easy. So let's just recall that if you look back at your formulas, the mean is equal to n times p. So in this instance, n is 10, p is 0.6. This is going to give us 6. And then our standard deviation, okay, let me pull up the symbol here, is equal to the square root, I'm just going to do this for the sake of time, the square root of n times p times q. Now q, recall, is 1 minus p. So for this instance, 1 minus 0.6 is going to give us 0.4. So we're going to have the square root of 10 times 0.6 times 0.4. Or that's the square root of, first of all, 2.4, and that's going to end up giving us 1.5492 if we round to 4 decimal places. All right, so let's look at 19. The probability that an egg in a carton is cracked or broken is 0.05. In part A, we want to find the probability that a carton, and I should say a carton, not a cartoon, a carton of a dozen eggs has all good eggs. Okay, so let's take a look at this. Let's notice that our probability of having a cracked or broken egg is always the same in every single case of an egg. It's always 0.05. So this is a binomial random variable. We either have a cracked or broken egg or we don't. Okay, so let's just identify things here. We're going to have a dozen eggs, so n is 12. Our probability of them being cracked or broken is 0.05. And of course, the probability that the eggs are not broken will be 0.95, 1 minus 0.05. Okay, so let's use our chart. We want to find the probability that we have all good eggs. That means that x is 0. There are no cracked eggs. So if we use our chart and look for the probability of having no cracked eggs, probability that x equals 0. Okay, well, let's go to our chart here for a minute. Probability that x equals 0, and down to n equals 12. Here's n equals 12. All right, and then here's 0. And of course, x is less than or equal to 0 is going to be the same as x equals 0 in this instance. Our 0.05 was our p, so we're good looking right here. Probability of having no cracked eggs is 0.5404. So if I go back, this is 0.5404. All right, now b, let's find the probability that at least one egg is cracked or broken in a single carton. Okay, now we've already got the probability that no eggs were cracked. So really the opposite of having no eggs cracked is to have at least one egg cracked or broken. So all we really need to do to find this probability in part C is do 1 minus 0.5404 and get that answer. And that gives us 0.4596. All right, so let's go to number 20. And I may have to use my paint program on this one. All right, so a continuous random variable x has a uniform distribution on interval -4 to 4. We want to sketch the density function. And to help us here, I'm going to stop this for a second and draw this so you don't have to watch me painstakingly try to draw. So in my paint program, I've drawn what this thing will look like. It goes from -4 to 4, and it's uniform, meaning that every single bar that we were to draw in a histogram will go to the same height uniformly across. So we get this rectangle. And of course, this should be straight. I'm just not very good at drawing with my mouse. So we have a nice rectangle from -4 to 4. Now, what I might ask you on a test is, what's the height of this rectangle? Let's remember, under any probability distribution like this, the area has to be 1. So if we look at this rectangle, remember that the area of a rectangle is always the length times the height, or the length times the width, whichever way we want to think about that. And if we look down here at the bottom, the length of this from -4 to 4 is actually 8 units. So this is 8 units across, which means that when we multiply it times the height of this rectangle, it has to be equal to 1. So this height has to be 1 over 8, the reciprocal. So right up here, this would have to be marked on the y-axis at 1/8 in order for us to have the proper area underneath that curve. Okay, so let me go back now to our next one. So that was number 20. Let's take a look at number 21. Now, unlike number 20, we have a continuous random variable with a normal distribution. So with a normal distribution, let's remember the shape is going to be a bell curve. And with a bell curve, the mean will be in the middle, and then our standard deviation of 20 will go out to the sides with multiples going out. And let me first draw it for you so you won't have to watch me again painstakingly trying to draw. Okay, so here's my bell curve. I want you to imagine that it's actually more symmetric than my attempt to draw it here on using a mouse, which is not so easy. But when we're talking about drawing a bell curve, we want to put the mean smack in the middle here. And then if we're one standard deviation away from the mean, in this case, our standard deviation is 20. If we go in this direction and add 20 to our mean, we'd be at 220. And if we subtract 20 from our mean, we'd be at 180. Now remember, the empirical rule, which applies to normally distributed or normal distributions, tells us that 68% of the data will fall between 180 and 220. So my red lines here are representing that 68% of the data fall between those two values. Now if we go out another standard deviation, adding 20 to 220, that gives us 240, and subtracting 20 from 180 gives us 160. Our empirical rule says that 95% of the data will fall between 160 and 240. Between these blue marks. And then if we go out a third standard deviation, adding 20, we get 260, and subtracting 20 over here, we get 140. And our empirical rule says that 99.7% of our data will fall between 140 and 260, these green marks on this curve. So if I ask you on a test, I will probably ask you to draw it on your own and then tell me how that empirical rule applies. You can say, for example, if I'm asking you about 3 standard deviations, 99.7% of the data is going to fall between 140 and 260. So those are the sort of things that you may have to report on the test. All right, now let's go back to our review sheet. I may or may not have time to answer the next one. We'll see. All right, so 22 is asking us to use Excel to find the probabilities. And yes, we should be able to do this very quickly on Excel. We want to find the probability that Z is less than negative 1.23 on Excel. All right, so let's pull up Excel and do that. So remember that our function in Excel naturally gives us, for the standard normal distribution, gives us the probability that X is less than a number. So when we put this one in, we're going to get the probability we need. So equal norm S dist is this one right here. And then we want to tell it negative 1.23 and the word true. And that tells us that probability is 0.1093. Now, if we go back and look at part B, in part B, we want the probability Z is greater than 2.34. Now, let's remember when we put 2.34 in this same function, it's going to give us less than. So we're going to have to subtract it from 1 to get greater than. So I'll go back, 2.34, we'll have equal norm dot S dot and 2.34 true. It gives us that, and let's just subtract that from 1. And there's our actual probability for greater than. Now, I hope I don't run out of time on this last one, but we'll go ahead and do this if we can. All right, so now we want to find the probability that Z is in between two values. So we need to find this probability using our formula and this probability, and then subtract the two answers to get a value in between. So 1.62 I'll do first. So equal norm, oops, wrong one. 1.62, true. And then my second one, and I do think I'm going to run out of time, but we will try real fast. Negative 2.10. Yeah, I did. Now I'm running out of time, so just I accidentally typed something wrong there, but we'll get that value and then subtract the two to get our final answer for that one. And And so so we could get the answer before we run out of time, this is our second probability, and if we subtract the two, we get 0.9295.